Hi, guys. Let's talk about space. I was trying to figure out how I can do this and you can see me at the same time. And I haven't quite figured that out yet. I'm sure that it's something real obvious that I don't know. So thank you for filling out your reflection. I was glad to see that some of you really enjoyed that project. It's good feedback for me, just not even for like what I'm going to do next year, but for me as a human. It's kind of fun to get feedback of things that are positive and also how things could have been better because I'm always trying to grow and figure out how to be a better human. So as we transition into space, I wanted to review a couple of the questions that I asked you, and then I was like, oh, this is a great teachable moment. So this was the results of the quiz. And at this point, you can see I did this today. So there were 68 responses in by the time I did this. And so some of you missed out on the responses. I'm sorry, I don't know how to help you. Within that, over 50% of you had the correct answer that the universe was 13.8 billion years old. The 4.5 billion, which was the second largest group of people, I tricked you. 4.5 billion is the age of our Earth. And so when we think about our solar system and where we live, 4.5 is a number you know. 500 million was the Cambrian. So I wondered if anyone would pick because it would sound familiar. And 700 billion I just made up. That's not even a thing. So just kind of seeing where you are. And so then the question becomes is how in the hell do we even figure out and know how old the universe is? So I thought I would tell you some of the current pieces of data that astrophysicists use to claim and provide evidence that the Earth is 13.8 billion years old. One of those pieces of evidence is globular clusters. And globular clusters are dense clusters of at least 1 million stars. So there's 1 million stars. And okay, with stars, one of the things that stars do is stars are born and then they go through a life cycle stage and then they die. So stars have a specific life cycle. We've got nebulas, we've got like the burning stars, and then eventually when it dies out, we could have white dwarfs, we could have red dwarfs, we could have black holes. And so there's this whole field that scientists have been gathering data about the life cycle of stars. You could definitely memorize it or you could just look it up, but it's a thing. So depending on the mass of the star determines how quick it goes through this life cycle. And so with mass and stars and burning and formation of gases, what's happening is hydrogen fuel. So the hydrogen in our universe, which is one proton, is fusing to make a bigger atom. So this is literally nuclei of atoms fusing. And as they do that, their energy, their color, things change about these stars. And so if I can look at these globular clusters and I can gauge the age of these clusters, I can come up with a life cycle. So these globular clusters have been given the acronym or the nickname cosmic clocks. I can use the life cycle of these stars to judge how age and how old the universe is. And the range that we have is 11 to 18 billion years old, which sounds ridiculously not accurate or at least precise. But again, when you're talking billions of years, plus or minus a billion, and then you're talking about we're taking data and analyzing data that we don't truly 100% understand yet. And we'll get there a little bit more. And I want you to keep remembering, you only know what you know when you know it. And so what we know so far about these globular clusters is it puts the age of the universe about 11 to 18 billion years old. Okay, well, that's pretty good. The other piece of data scientists use is that our universe is expanding. The universe is getting bigger and bigger and bigger and bigger and bigger. And so you had this idea that there was this big bang. So there was this nothingness, a pinpoint of matter. and then an explosion, and all the matter in the universe that ever has and ever was and ever will be came from this big bang. Where did the matter come from? For that, we don't know. The answer is we don't know. And so astrophysicists can obviously have predictions, write hypotheses, and show a little bit of evidence. But when they don't know, they say they don't know. They're not going to make up a story. There can be different sort of camps of astrophysicists depending on which mathematical formulas they're looking at, and we'll get there in a minute. So the universe is expanding, and we can use a measurement called the Hubble constant to calculate how fast the universe is expanding. And depending on which numbers you use, you're going to get a slightly different values. But when we calculate how fast is our universe actually expanding and accelerating, then we can count back to where the beginning was. So these two mathematical calculations are helping us say we claim the universe is this old, and here's why. Next, second question that you guys answered, our knowledge of the universe comes from guessing. Although, maybe. Physics, chemistry, and space exploration. And I kind of did this on purpose because I knew a lot of you would say space exploration. And I do want to talk about the fact that, y'all, we don't know jack. I mean, we do, but the amount of things we don't know. So you know how people are like, oh, we know more about space than we know about the ocean? And we really don't. There is so much out there that we cannot explain because we don't have the tools to understand it. That's kind of cool when you think about it. So in this question, I was thinking physics and chemistry with the theoretical physics and chemistry, either one of those, and many of you picked physics. But with space exploration, we haven't really got very far. Let's look. There's ways that scientists work. One of those ways is called theoretical. Theoretical means I take calculations, I plug them into formulas, I try to make relationships, I look at the relationships between variables, and I do what's called theoretical physics. Theoretical physics looks like this. It's very mathematical. People sit in the lab and they do theoretical physics all day, all day, all day, all day, all day. These theoretical physicists, aka Albert Einstein, literally spent years and years of their lives, hours each day, looking at mathematical calculations of relationships between variables. As this variable does this, what does this variable do, and how can I make that fit? Or how does it fit? And so with theoretical physicists, they'll say, okay, in the mathematical world, this is what happens, but we don't really know until someone can measure it. So with Albert Einstein 110 years ago, he came up with these ideas about, you guys, I think that the universe is not empty space. I think that space isn't space. I think space is this fabric. And he created these mathematical calculations to show his theory. We've since collected data that supports his claim. Scientists have collected experimental data that supports Einstein's theory of relativity. When the first picture of the black hole was ever taken from the radio wave collection and then transformed into a visible picture, you'll learn about that in 8th grade. That supported Einstein's theories. Einstein theorized what that black hole would look like, but no one had ever collected experimental data. Space science is very much a mixture between experimental data on the left here and theoretical data on the right. And so remember with Hidden Figures, Katherine Johnson, she's on the right. Maria Mitchell's on the left. And so Maria Mitchell was a experimental astronomer. She sat and observed the night sky for hours and hours and hours and years and years and years. She actually discovered a comet. She's credited for a lot of really good work. Maria Mitchell, if you want to look her up, she has a decent autobiography. She often is left out of books, and you can probably guess why. She's a girl. So we are, in a world where we're starting to identify women have had a lot of positive influence on science. It's just the books weren't written by them. They were written by the men, and therefore they got left out. It's a very common thing. Maria Mitchell sat and looked. She did the experiments. She was out in the field. Katherine Johnson sat in the laboratory and calculated physics to figure out the relationships in this astronomical world, helping those Apollo astronauts succeed in their mission. This is a picture of, okay, how much do we really know? So if the above picture is the Milky Way galaxy, which is our galaxy that we live in, imagine that our entire solar system, so our solar system in the Milky Way was the size of a quarter. The sun within that solar system is a microscopic speck of dust, as are its 9 planets, whose orbits are represented by the flat disk of the coin. So we often think of our solar system as the sun being huge. And as I started learning and discovering more about the solar system, it is way, way, way more interesting than sun, 8 planets, oh yeah, Pluto, couple comets, asteroid belt, moons. There's so many more cool anatomical features, structures in our solar system that we don't even think about. And its vastness is so much more amazing. So if this were our solar system, this coin, and our planets and sun is a microscopic piece of dust, how far away is the nearest star in this model? The nearest star to us is Proxima Centauri. And if that nearest star has planets orbiting it, it would be in the real, like in our model here, this quarter, a second quarter, 2 soccer fields away. Can you imagine putting a quarter on a soccer field and then measuring 2 more soccer fields and putting a quarter and then trying to figure out where and mapping that? It is vast. It is so vast that your Homo sapien brain, the neurons that make up your brain tissue, cannot fathom the vastness of the universe. I think it's amazing. This, however, has been a really great addition to our knowledge of the universe and what's out there. This is the Hubble telescope, and it is a telescope that is orbiting around the Earth in where like the satellites are. So it's out past the atmosphere, which does help with a lot of clarity using a telescope. And it was out there looking for things. And I want to show you this story. Oh no, here, I want to do this. And I want to do this.
Since the Hubble Space Telescope went into orbit back in April 1990, it has sent back a ton of incredible photos.
Lit Mobile just sent me this wireless solar power bank. Let's see what's inside. Power bank has 20,000 milliamps.
Each has its own story, but one of Hubble's greatest images is this one from 1995. This is a snapshot of nearly the entire history of the universe, and the first of its kind. The Hubble Deep Field is an unusual image that came from an unusual process. Typically, astronomers apply to use Hubble to look at a particular known object. You want to study a star? Okay, you know what star you're going to study. You point the telescope at that star. That's Robert Williams. He became director of the telescope in 1983. It was his decision to create the deep field image by pointing the telescope at nothing in particular. What we were doing basically was just the opposite. We were trying to find sort of an indiscriminate area of the sky where no observation had been made before. They wanted to test how well Hubble could survey very distant galaxies, but they didn't know what they'd see, and it wasn't a great time to be trying new things.
After spending $2 billion for 12 years to have this kind of unexpected, very large mistake take place.
The Hubble team was still repairing the reputation of the telescope after a flaw in the main mirror produced blurry images for nearly 3 years. We were the butt of jokes and the newspapers, political cartoons, the Johnny Carson show. NASA was being made fun of for having made such a monumental screw-up of such an expensive project. NASA sent astronauts on a 5-day mission to install a module that would fix the problem, and it worked. So Williams' team spent 1995 planning the deep field observation. For one thing, they had to decide where to point the telescope. The goal was to see far beyond our galaxy, so the spot needed to be away from the galactic plane of the Milky Way and away from any known large galaxy clusters. They didn't want anything bright to block the view. And to get continuous observations, it needed to be a location that wouldn't be obscured when Hubble went around the Earth, as it does every hour and a half or so. They settled on a region just above the Big Dipper, a dark, unremarkable peephole into the universe. The field of view was extremely narrow. Astronomers measure the apparent size of objects in the sky in angular degrees, and a degree can be divided into 60 arc minutes. From Earth, the moon is about half a degree across, around 30 arc minutes. But the area that Hubble photographed was just 2.6 arc minutes across. A little larger than a pinhead at arm's length. It's a teeny patch of sky. The observations began on December 18, 1995, collecting 4 different wavelengths of light. And over the next 10 days, the telescope took 342 images of that teeny patch of sky. We were relieved that we were getting good data, but we had to keep adding it up. And so it wasn't until 10 days that we realized, we really got something. There are a few nearby stars in the image, but pretty much all the other objects here, including these tiny blue dots, they're galaxies. The light from these different galaxies has been traveling for vastly different amounts of time. So the furthest galaxies are shown pretty early in their evolution, more than 12 billion years ago. That's just 1.5 billion years after the Big Bang. It's as if you could point a telescope across the Earth and actually photograph ancient Egypt with a Neanderthal in the background, and then further back there's a dinosaur. The research team sampled another tiny spot 2 years later, this time in the southern sky. We wanted to know, we got one spot of the sky. You never know. Maybe it was some weird spot. So we thought it was important to repeat the observation. The datasets boosted estimates of the total number of galaxies. They allowed researchers to track the history of star formation through the universe, and they helped confirm the bottom-up theory of galaxy formation by revealing galaxies that are small and irregular early in their evolution. But one of the most important legacies of the Hubble Deep Field is how it changed the culture of astronomy. Until this time, astronomy had a history of people taking the data and keeping it to themselves until they had fully analyzed it. After all, this is intellectual property. Instead of hoarding the discoveries embedded in the data set, Williams and his team formatted and released it immediately to the wider scientific community. It's been cited in hundreds of papers. Nowadays, it is much more common for people to take interesting observations and make the data available to the public, even though they might have a right to keep it for a certain period of time to themselves. Thanks to servicing missions that installed more advanced cameras, Hubble has since made even deeper deep field images, and those data, too, were released to the public. I think it moves forward the march of human understanding, human knowledge, tremendously, and the Hubble Deep Field did that.
How is that for amazing? Right? Did you see all those galaxies? You had no idea. They had no idea. They pointed to a blank space in the sky, like, oh, there's nothing there, let's just see. And lo and behold, millions of galaxies. Just incredible. The next question that you guys answered were scientists know exactly where the material for the Big Bang came from, and 92% of you answered this correctly. That is false. We do not know. And some of you said true. Okay, let's see why we don't know what we don't know. So here we see this is a Hubble telescope image. And so again, that Hubble went up, and after they fixed the flaw of the blurry photographs, which was definitely an embarrassment, it's been there taking thousands of images. So you, in your PhD program and your astrophysics work, can apply to use and point the Hubble somewhere. It's kind of like applying to use a supercomputer. You can, say, oh, I want to set up time for this date, blah, blah, blah. So of all that we know, of all the stars and the planets and the galaxies that can be seen today, it's just 4%. 96% of the universe is made up of stuff that we can't see, that we don't know how to measure, that we don't understand. And so when it says can't detect, they're saying like we don't have the tools to detect it's out there. And so think about like how that applies to something you know. Okay, well, in the 1600s, when people got sick with a cold, you are a sinner, you have sinned, and you now are sick. No, it's bacteria and viruses, but they had no way of knowing that. There was no tools to gather that data to interpret. And so there you go. You only know what you know when you know it. And with our current tools, there is 96% of stuff we don't know.
Matter as we know it. Atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% dark energy, both of which are invisible. This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So, what do we know? Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there's just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. The stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it, kind of. Places with a high concentration of dark matter bend light passing nearby, so we know there's something there that interacts with gravity. Right now, we have more ideas about what dark energy is not than what it is. We know dark matter is not just clouds of normal matter without stars because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know three things for sure. 1. Something is out there. 2. It interacts with gravity. 3. There is a lot of it. Dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in a way we expect, but right now, we just don't know. Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it, but we do see its effects very clearly. In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts towards the red end of the electromagnetic spectrum as it travels through space. He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much. Hubble determined that this was because the universe itself is expanding. The redshift occurs because the wavelengths of light are stretched as the universe expands. More recent discoveries have shown that the expansion of the universe is accelerating. Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point. Space doesn't change its properties as it expands. There's just more of it. New space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know, and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined. We have multiple ideas about what dark energy might be. One idea is that dark energy is not a thing, but just a property of space. Empty space is not nothing, it has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that just more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of a concept of a cosmological constant, a force that counteracted the force of gravity. The only problem is that when we tried to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion. Another idea is that empty space is actually full of temporary, virtual particles that spontaneously and continually form from nothing and then disappear into nothing again. The energy from those particles could be dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field which permeates the entire universe, but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where, or how we could detect it. So there are still a lot of questions to answer. Our theories about dark matter and dark energy are still just that, theories. On the one hand, this is kind of frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones, on a tiny, fragile island in space, looking into the sky, wondering how our universe works. There is so much left to learn, and that is awesome.
This graphic right here is one of my favorites. So in the middle is what we know. In that circle, towards what we know is what we don't know. And then everything else is what we don't know that we don't know. We don't even know what we don't know. What? You guys, this is crazy and awesome and fun because your generation is gonna figure this out. So when I asked you on a scale of 1 to 10, how important is it to know about space? The most of you were between a 7 and a 10. A couple of you did not think it was important at all. And we're a variety of opinions in our species of Homo sapiens, and so that's okay. Those of you that think that it's important to know about space, I'm excited for you to learn more about what we know, what we don't know, and what we don't know we don't know.